Hello viewers, I am Asghar Pasha, Assistant Professor, Department of Mathematics, MS Ramaya Institute of Technology, Bangalore. Today I will be solving problems on Legendre's differential equation, which is a continuation of my last session, and also I will talk about solution of first order nonlinear differential equations. Problem number 5. Solve 2x plus 1 whole square d square over dx square minus 2 into 2x plus 1 into dy by dx minus 12y equals to 6x plus 5. You can see the coefficient of d square over dx square is 2x plus 1 the whole square, and coefficient of dy by dx is 2x plus 1, and coefficient of dependent variable y is constant. So it is Legendre's differential equation. This is a differential equation with variable coefficients. This can be converted to a differential equation with constant coefficients using the substitution 2x plus 1 equals to e to the power of t. So with this substitution, t becomes log of 2x plus 1, and when you simplify this in terms of x, this becomes x equals to e to the power of t minus 1 divided by 2. So with this substitution, the variable coefficients like 2x plus 1 into dy by dx becomes a into dy. A is 2 here, the coefficient of x, and 2x plus 1 whole square d square y by dx square becomes a square. A is 2, so it is 4 into d minus 1 y, where d represents derivative with respect to new variable t. If we substitute all these things in the given differential equation, we get 4 into d minus 1y minus 2 times 2 dy minus 12y equals to 6 into x. This is the x part, which is e to the power of t minus 1 divided by 2 plus 5. Simplify this to get this term. D square 4 times d square minus d minus 3 of y equals to 3 e to the power of t minus 3 plus 5. So after simplification, we get a differential equation with constant coefficients. D square minus 2d minus 3 of y equals to 3 by 4 into e to the power of t plus 2 by 4, which is 1 by 2. Now write auxiliary equation, which is m square minus 2m minus 3 equals to 0. Solve this equation to get roots as m equals to minus 1 and plus 3, and write CF C1 into e to the power of minus t, which is a part of CF corresponding to real root minus 1, and C2 into e to the power of 3t, which is part of CF corresponding to the root m equals to plus 3. Now you write e to the power of minus t as e to the power of t whole to the power of minus 1, e to the power of 3t as e to the power of t whole cube, and substitute e to the power of t as 2x plus 1 to get CF in this form. CF is C1 divided by 2x plus 1 plus C2 into 2x plus 1 the whole cube. Now let us find Pi. Pi is 1 divided by f of d, which is d square minus 2d minus 3 operated on 3 by 4 e to the power of t plus 1 by 2. I will separate this. I will treat this half as a half times e to the power of 0t. So I will operate f of d on both of this to get 3 by 4 times pi1 plus half of pi2. Let me find pi1 first. pi1 is 1 divided by d square minus 2d minus 3 operated on e to the power of t. It is type 1. According to type 1, we have to replace d by a. A is coefficient of t here, which is 1, provided denominator is not equal to 0. If we replace d by 1, we get 1 minus 2 minus 3 e to the power of t, which is equals to e to the power of t divided by minus 4. This is pi1. Now consider pi2. pi2 is 1 by d square minus 2d minus 3 operated on e to the power of 0t. Now we have to replace d by 0, and denominator becomes 0 minus 3 e to the power of 0t, which is nothing but minus 1 by 3. So particular integral is 3 by 4 into pi1 this is pi1 term plus half into pi2 term. You simplify this to get minus 3 e to the power of t by 16 minus 1 divided by 6. Now convert t in terms of x. Pi is minus 3 into 2x plus 1 divided by 16 minus 1 by 6. Therefore, required solution is y equals to Cf plus Pi. Problem number 6. Solve 2x plus y the whole square into d square y by dx square minus 6 into 2x plus y into dy by dx plus 8y equals to 6x. You can see coefficient of d square over dx square is of the form ax plus b whole square. Coefficient of dy by dx is some constant into ax plus b, and coefficient of y is constant equals to 6x. This is Legendre's differential equation. This equation can be converted to a differential equation with constant coefficients, linear differential equation with constant coefficients using the substitution 2x plus 5 equals to e to the power of t, so that t becomes log of 2x plus 5 and x becomes e to the power of t minus 5 divided by 2. With this substitution, terms like 2x plus 5 into dy by dx gets converted to 2 into dy. 2x plus 5 whole square d square y by dx square gets converted to a square into d minus 1 into y, where a is 2. So 2 square is 4, 4 into d minus 1 y, where d represents a derivative with respect to new variable t. Substitute all these things in the given differential equation. We get 4 times d into d minus 1y, which is second order derivative, minus 6 times 2 dy, which is first order derivative, plus 8y equals to 6x. X is e to the power of t minus 5 divided by 2. Multiply 4d, it is 4d square minus 4d, multiply 6 minus 12d plus 8, take y outside, that is equals to 3 times e to the power of t minus 5. You simplify this to get this form, d square minus 4d plus 2 of y equals to 3 by 4 times e to the power of t minus 15 by 4. This is linear differential equation with constant coefficients. So solution of this differential equation can be determined by finding Cf and Pi. As you know, Cf is a solution of homogeneous part of the differential equation. So consider auxiliary equation, which is m square minus 4m plus 2 equals to 0. You find its roots, which are 2 plus or minus root 2. So roots are real and distinct. Real and distinct roots. M1 is 2 plus root 2 and M2 is 2 minus root 2. This is a part of CF corresponding to M1, which is 2 plus root 2, and this is a part of CF corresponding to M2. So CF is C1 times e to the power of 2 plus root 2t plus C2 times e to the power of 2 minus root 2 into t. Now use law of indices. You can write e to the power of 2 plus root 2 into t as e to the power of t whole to the power of 2 plus root 2, and e to the power of 2 minus root 2t as e to the power of t whole to the power of 2 minus root 2. Now substitute, convert t in terms of x using the known substitution. E to the power of t is 2x plus 5. So CF is C1 times 2x plus 5 whole to the power of 2 plus root 2 plus C2 times 2x plus 5 whole to the power of 2 minus root 2. Now particular integral. It is 1 by f of d. F of d is d square minus 4d plus 2 operated on the RHS part, which is independent of x. It is 3 by 4 independent of y, and we have converted x in terms of t. So RHS will be a function of t. 3 by 4 e to the power of t minus 15 by 4. I will write this 15 by 4 as 15 by 4 into e to the power of 0t. So, separate pi. Pi will be 3 by 4 times pi1 minus 15 by 4 times pi2. Consider pi1, which is 1 by d square minus 4d plus 2 operated on e to the power of t. Type 1, just replace d by 1, the coefficient of t. So, if we replace d by 1, we will get 1 by 1 minus 4 plus 2 operated on e to the power of t. So, answer is minus e to the power of t. Consider pi2, 1 by d square minus 4d plus 2 operating on e to the power of 0t to give 1 by 2. So, pi is 3 by 4 into e to the power of minus t minus 15 by 4, 1 by 2. Simplify this to get pi equals to minus 3 e to the power of t by 4 minus 15 by 8, and then convert t in terms of x to get pi in this manner. Pi is minus 3 times 2x plus 5, because e to the power of t is 2x plus 5. So, pi is minus 3 times 2x plus 5 divided by 4 minus 15 by 8. The complete solution is y equals to Cf plus pi. This is solution of Legendre's differential equation. In case if boundary conditions are given, boundary conditions specified at more than one point, for example, y of a equals to some ya and y at b equals to yb is given. Two conditions are given, conditions specified at 2 points a and b. More than one point is a boundary condition and corresponding problem is known as boundary value problem. If these two conditions are given, you have to find the particular solution by substituting this in the general solution, and you have to determine the arbitrary constants C1 and C2. Instead of boundary conditions, initial conditions may be specified. What are initial conditions? Conditions specified at a single point. Maybe like this: y of a, y at a equal to some ya, and one more condition is required, and that condition may be like this: y dash of a equal to some yb, something like this. Condition specified at a single point a. If initial conditions are given, then you get one equation. When you substitute x equals to a here and y equals to ya here, you will get one equation in terms of C1 and C2. Next, you differentiate this equation with respect to x and then substitute the second condition, y dash of a equals to yb. You will get one more equation in terms of C1 and C2. Solve those two equations and substitute in the general solution to get the required particular solution. So, this is about Legendre's differential equations. Now, I will find solution of first order non-linear differential equation. You are already familiar with the linearity concept. You know that a differential equation with constant coefficient of this form, some an into nth derivative plus an minus 1 into n minus 1th derivative plus dot plus some a1 into y plus a naught equals to phi of x, whatever it may be. You can take a naught to the RHS so that LHS contains terms of dependent variable as well as derivatives with respect to dependent variable only. This will be linear provided an is a constant. If an, ai, all ai's are constants, are functions of x alone, only x. If an, if any one constant, if any one ai is a function of y, then you will be having y into derivative term, product of y into derivative or y into y square, which makes this equation non-linear. So, these are all, this is nth derivative, but degree is still 1. Even if all ai's are constants, or if all ai's or constants are function of x, this equation still becomes non-linear if degree is more than 1. Now I have an equation of the form p to the power of n plus a1 into p to the power of n minus 1 plus a2 into p to the power of n minus 2 and so on p plus an equals to 0, where p stands for dy by dx and ai's are functions of x and y. So definitely this is a non-linear differential equation. Two reasons. Reason number 1, p to the power of n, terms like p to the power of n, p to the power of n minus 1. So degree of these terms are not 1. It's like dy by dx whole to the power of n. Next, p to the power of n minus 1, dy by dx whole to the power of n minus 1 and so on. As degree is not equal to 1, definitely it is non-linear. And there is one more reason. We have specified that ai can be a function of y. So if it is a function of y, product of dependent variable and derivative exists, and it will be no more a linear equation. I'll give you examples of linear and non-linear equations. If I write like this, 2x into dy by dx plus y square equals to cos x, then this is a non-linear differential equation because of this power y square. This product can exist because it's a product of independent variable and derivative. Only because of this power, this differential equation is non-linear. Let me take one more example. Y into d square y by dx square plus 4x into dy by dx plus 6y equals to e to the power of x. This is a non-linear equation because of this product term y into d square y by dx square. This is a non-linear differential equation of second order. Okay. What is non-linear differential equation of first order? It will be like this, dy by dx, power can be anything, 4 plus coefficients can be anything, 2xy dy by dx, only first order derivatives, power can be anything, equals to some function e to the power of x. This is a non-linear differential equation of first order. You can see derivative of y, dy, there is no d square d cube terms, dy by dx, order is 1 but power is 4. This is a non-linear differential equation of first order. Now how to solve such equations? There are many techniques depending on the nature of the equation, whether it is solvable for x, solvable for y or solvable for p, or it is in some standard form. Depending on that, we can decide whether it is solvable for or not. Suppose the given differential equation of this type, first order, p indicate dy by dx, so it's a first order only. These are all degrees, nth degree, n minus 1th degree, n minus 2nd degree and so on. So non-linear differential equation of degree n, you can treat it as a polynomial of degree n, so it will have n roots. You just factorize them like this and equate it to 0 and solve each of this. When you equate it to 0, you get p minus f1 of x comma y equal to 0. P is dy by dx minus f of x comma y equal to 0. So it's a first order, first degree differential equation. You can find its solution by known technique, maybe by variable separable form or homogeneous type or exact differential equation or any method that you have studied. So you can easily solve n first order, first degree differential equations. Let f1, f2, etc. fn be solutions of these n differential equations. It may be solution may contain arbitrary constant c1, here c2, c3. I have written c throughout because without loss of generality I can assume c throughout. Even if it contains c1, c2, c3, etc. cn, in the final solution without loss of generality you can replace them by one constant c, because finally it is a differential equation of first order, and as you know, general solution of first order differential equation contains only one arbitrary constant and hence only one C. Throughout, only one constant C, arbitrary constant C. So the rule is, if this equation, first order and nth degree equation, is said to be solvable for P if you can find roots, if you can solve it for P, if you can factorize it, and you get equation of the form P minus f1 of xy equal to 0, P minus f2 of xy equal to 0 and so on. If it is possible, factorize this in terms of P, find its roots, and then convert this into n first order first degree differential equations, find solutions to all those n equations, and product of this solution will be general solution of the given nth degree non-linear differential equation. I will illustrate through an example. Problem number 1, solve dy by dx whole square minus 7 dy by dx plus 12 equals to 0. You can see there is a second degree term here, dy by dx whole square. Write dy by dx as p to get p square minus 7p plus 12 equals to 0. It is easily factorizable. You can write minus 7p as minus 4p minus 3p so that its product is 12p square, and factorize it to get roots as p equals to 4 and p equals to 3. This is dy by dx minus f1 of xy equal to 0 and dy by dx minus f2 of xy equal to 0. Two first order first degree differential equations. Consider p equals to 4. You know that p is dy by dx. Dy by dx equals to 4 is a first order and RHS is constant, so you can easily get its solution by direct integration. You integrate it to get solution as y equals to 4x plus c. Therefore, y minus 4x minus c equals to 0 is solution of p equals to 4. Consider p equals to 3. Dy by dx equals to 3, integrate it to get y equals to 3x plus c. Therefore, y minus 3x minus c equal to 0 is a solution of second differential equation. Thus, the general solution is product of these two solutions, which is y minus 4x minus c into y minus 3x minus c equals to 0. Problem number 2. Solve p square plus 2py cot x equals to y square. Given differential equation is p square plus 2py cot x minus y square equal to 0. It's like x square plus ax square plus bx plus c equal to 0. So find its roots using the formula minus b plus r minus root of b square minus 4ac divided by 2a. You can see this is b. The coefficient of p here is p, b, which is 2y cot x. So I have written minus b plus r minus root of b square part 4y square cot square x minus 4ac, which is 4y square divided by 2. Simplify this. Take 4i square outside the square root to get 2y. Then it is 2y into root of cot square x plus 1. Cancel 2 and write this as cosecant x. You know that 1 plus cot square x equals to cosecant square x. Therefore, root of cot square x plus 1 is cosecant x. So, two roots. One is minus y cot x plus y cosecant x, and another one minus y cot x minus y cosecant x. We have to solve these two equations. Consider first factor. P equals to minus y cot x plus y cosecant x. Take y outside, it becomes cosecant x minus cot x. You can solve this differential equation using variable separable method. Separate x and y terms. It is dy by y equals to cosecant x minus cot x into dx. Now it is in separable form. Integrate it. Integration of 1 by y is log y, and integration of cosecant x is log of tan of x by 2, or else you can write it as minus log of cosecant x plus cot x, or log of cosecant x minus cot x. In any form you can write integration of cosecant x. I have written it in simple form, which is log of tan x by 2, and integration of cot x is log of sin x, and I have taken arbitrary constant as log c, because any constant k, whether it is positive, negative or 0, whatever it may be, any real number k can be written as log a. Log a can be negative, but log of a does not exist if a is negative. Log of negative number does not exist, but log a in total can be negative. So the arbitrary constant k can be written as log c. Now use properties of logarithms. You know that log a plus log b minus log c equals to log of ab divided by c. I have used this result here, log a minus log b plus log c. So it is log of a into c divided by b. So log y equals to log of tan of x by 2 into c divided by sin x. Simplify this. You get y equals to tan x by 2 divided by sin x into c. You can write tan x by 2 as sin x by 2 divided by cos x by 2, and this sin x can be written as submultiple formula 2 sin x by 2 into cos x by 2. You just cancel this sin and take cos to denominator. It becomes 1 by 2 cos square x by 2, and you know that 2 cos square theta equals to 1 plus cos 2 theta. Theta is x by 2 here. So 2 theta is x. So 2 cos square x by 2 is 1 plus cos x into c. Simplify this, cross multiply to get this solution for the first factor. Y into 1 plus cos x equals to c. Now let us consider second factor, which is p equals to minus y cot x minus y cosecant x. In the first factor there was plus here, now it is a minus. So what difference it makes? P can be written as dy by dx. Take minus y outside, you will get minus y into cosecant x plus cot x. You separate x and y terms, it will be dy by minus y equals to cosecant x plus cot x into dx. Now it is in separable form. Integrate it. You can write integral of 1 by y as log y. As usual, integration of cosecant x is log of tan x by 2. Integration of cot x is log of sin x, and I have taken arbitrary constant as log c, and the reason is justified. I have already told you. You can take it as log c so that I can easily get y. Now I have used the properties of logarithm here. Minus log y can be written as log of y to the power of minus 1. Because of this result, b into log a equals to log of a to the power of b. So it is log of y to the power of minus 1 equals to, now properties of logarithms, log a plus log b plus log c equals to log of ab into c. Now y to the power of minus 1, which is 1 by y, equals to tan of x by 2 into sin x into c. You can write tan of x by 2 as sin x by 2 divided by cos x by 2, and the sin x can be written as 2 sin x by 2 into cos x by 2. As usual, you simplify this, cancel cos x by 2, you will get 1 by y as 2 times sine square x by 2 into c. And you know that 2 sine square theta equals to 1 minus cos 2 theta. Here theta is x by 2, so 2 theta is x. Therefore, 1 by y becomes 1 minus cos x into c. Cross multiply, it is 1 by y into 1 minus cos x equal to c, or after simplification you get this y into 1 minus cos x equals to 1 by c. I will take this 1 by c as k. It is y into 1 plus cos x minus k equal to 0. Observe that I have written k here. And in the solution for the first part of the equation, I have written c. So, 2 arbitrary constants I have written, but ultimately when you are going to write general solution, you should write only one arbitrary constant. So, there is, without loss of generality, I can write this k as c. Therefore, solution of the given differential equation is y into 1 plus cos x minus c, which is solution of the first part, and y into 1 minus cos x minus k. Instead of k I have written c, because general solution of first order differential equation must contain only one arbitrary constant. Now, problem number 3, solve p into p plus y equals to x into x plus y. This is first order and a higher degree differential equation. Degree of the differential equation is 2, p square term, and it is solvable for p because it is quadratic equation. As you can see, it's a quadratic equation in p with a as 1, b as y, and c as minus of x square plus xy. Use the formula minus b plus or minus root of b square minus 4ac divided by 2a to get this. Simplify this, y square plus 4x square plus 4xy. This is nothing but a plus b whole square type. So, it is y plus 2x the whole square, and root of y plus 2x the whole square is just y plus 2x. So, p is minus y plus 2x divided by 2x square and minus y minus of y plus 2x divided by 2 square. So, 2 factors. Consider first one, simplify it to get p equals to 2x by 2. Second one, if you simplify, you will get it as minus 2y minus 2x by 2. Therefore, 2 first order first degree differential equations are p equals to x and p equals to minus y minus x. Consider p equals to x. P is dy by dx equals to x. So, dy becomes x dx integrated. As only x is here and only one derivative, you can easily get its solution by direct integration. Integration of dy by dx equal to x is y equals to x square by 2 plus c. You simplify this to get solution in this form, 2y minus x square minus c equals to 0. Now, consider second factor, which is p equals to minus y minus x. P is dy by dx minus y minus x. This implies dy by dx plus y equals to minus x. This is Leibniz linear equation. You know that a first order differential equation of the form dy by dx plus p of x into y equals to q of x is known as Leibniz linear differential equation, and its solution is dependent variable y into integrating factor equals to integration of right hand side with respect to independent variable plus one constant of integration, where, okay, I have not written if here, q of x into if, q of x into if with respect to x plus constant of integration, where if is e to the power of integration of p of x dx. P is coefficient of y here. Why it is called as integrating factor? When you multiply this equation by e to the power of integral of p of x into dx, this equation become exact. Okay, and you can easily find its solution by direct integration. If it is exact, then it is du equals to something, then its solution is u equals to constant directly. So this becomes exact if you multiply this throughout by e to the power of integral of p of x into dx. Now you can see here dy by dx plus y equals to minus x. P of x is coefficient of y, which is 1, and this part is q of x. So this is a Leibniz linear equation. Integrating factor is e to the power of integral of p dx. P is 1 dx, and here integration of 1 is x, e to the power of x. Don't write arbitrary constant here, it's of no use. Even if you write constant here, it will be e to the power of x plus some constant, and that can be written as e to the power of x into e to the power of c. And when you write that here and divide by e to the power of c, you will get c by e to the power of c, some other constant. So it's of no use. So when you are finding if, there is no need to write c, constant of integration, it's not required. So I have determined integrating factor, which is e to the power of x. Now solution of this Leibniz equation is y into integrating factor equals to integration of right hand side, which is minus x, into integrating factor with respect to independent variable plus constant of integration. Now write if is e to the power of x, y into e to the power of x equals to integration of minus x into e to the power of x dx plus c. Now you integrate this by parts or Bernoulli's rule, which is extension of parts, to get this. You know that Bernoulli's rule, integration of u into v dx equals to, write first function as it is, you integrate the second function u into v1 minus differentiate first function, integrate second, plus alternatively plus and minus, differentiate first, integrate the second one, and so on, continue like this. Of course this is never ending if u is some trigonometric function, derivative of any order exists. So this method is suitable when u is a polynomial, so that its some certain order derivative becomes constant and all higher order derivatives after some stage become 0. That is, if u is a polynomial of degree n, its nth order derivative will be constant, and all derivatives of order greater than n are 0. So it's best suited when first function is a polynomial and second one, of course, easily integrable. For example, if you have integration of x square into cos 4x dx, if you want to apply parts, you have to apply it twice. But if you use Bernoulli's rule, you can write its solution in one single line. First function as it is x square, integration of second function, integration of cos 4x is sin 4x divided by 4, minus differentiation of x square, first function, differentiation of x square is 2x, into integration of second function, integration of sin 4x is minus cos 4x divided by 4. 4 into 4 is 16 plus. Now differentiate 2x. Derivative of 2x is 2. Now integrate it. Integration of cos 4x is sin 4x by 4, minus remains as it is. Integration of cos is sin 4x divided by 4. So it is 4 into 16 minus differentiation of 2, 0. Stop. So this is easy when power of x is more. Otherwise, if it is x cube, you have to apply parts 3 times, x power of 4 4 times, and so on. Whereas in Bernoulli's rule, you can get answer in a single step. So prefer Bernoulli's rule in such cases. This is x into e to the power of x dx, x power of 1, polynomial of degree 1, anything. I have used Bernoulli's rule here. You can see minus I have taken outside. First function as it is. Integration of e to the power of x is e to the power of x minus sign according to the rule, and I have written 1, which is derivative of x into integration of e to the power of x, second function, and again derivative of 1 is 0. So stop the process. You get this as solution. Y into e to the power of x equals to minus x into e to the power of x plus e to the power of x plus c. Simplify this to get e to the power of x into y minus 1 plus x minus c equal to 0. Therefore, general solution is product of these two solutions, 2y minus x square minus c equals to 0 into e to the power of x into y minus 1 plus x minus c equals to 0. Problem number 4. Solve dy by dx minus dx by dy equals to x by y minus y by x by solving for p. You write dy by dx as p, so that dx by dy becomes 1 by p, it's reciprocal, and that is equals to x by y minus y by x. P is dy by dx and 1 by p is dx by dy. There are two techniques of solving this. One, you can factorize it by using by solving quadratic equation xy into p square minus p into x square minus y square minus xy equal to 0. B is minus of x square minus y square, so this is minus b plus or minus root of b square minus 4ac divided by 2a. You just solve this. P equals to x square minus y square plus or minus root of x to the power of 4 plus 2x square y square plus y to the power of 4 divided by 2xy. This is nothing but x square plus y square the whole square under the root, and after that when you simplify it, you will get two roots as p equals to 2x square by 2xy and p equals to minus 2y square divided by 2xy. You simplify this. P is x by y and one more root is minus y by x. I will tell you a shortcut method of doing this. The given differential equation was like this: dy by dx minus dx by dy equals to x by y minus y by x, or y by x minus x by y, vice versa, whatever it may be. I can call this as a. Dy by dx is a, then dx by dy is reciprocal of that, a minus 1 by a. I will call x by y as b, and in that case y by x will be reciprocal of x by y, which is 1 by b. You can see a minus 1 by b equals to b minus 1 by b. And this arrangement is possible in two cases. A minus 1 by a equals to b minus 1 by b in two cases. If a equals to b, straightforward. A equals to b means what? Dy by dx equals to x by y, which is here. P equals to x by y, dy by dx equal to x by y. This is one possibility. Or A equals to minus 1 by b. You just remember this. If a minus 1 by a equals to b minus 1 by b, then a can take two values like this. One is a equals to b and a is minus 1 by b. A is dy by dx, so dy by dx equals to b. b is x by a, one possibility, and another possibility is a equals to minus 1 by b, so p equals to minus of y by x, minus 1 by b. These are the two possibilities. So I have used both the definitions here, both the concepts. You can use any one of these to get roots of the given differential equation, which is solvable for p. Now solve these equations. First one is p equals to x by y. P is dy by dx equals to x by y. You separate the variables. Y dy equals to x dx. So equations are in separable form. Y dy equals to x dx. You can get its solution by direct integration. Integrate it. Y square by 2 equals to x square by 2 plus c, and then multiply by 2 to get y square minus x square minus 2c equals to 0. Consider the second factor, p equals to minus y by x. So it is dy by dx equals to minus y by x. As usual, separate the variables and integrate it. We get dy by y equals to minus 1 by x into dx. Integrated dy by y, integration of 1 by y is log y minus 1 by x, which is minus log x, plus some constant of integration log c. We can write minus log x as log of x to the power of minus 1 plus log c as it is. Now this is using properties of logarithms. Log a plus log b is log of ab. Therefore, y equals to x to the power of minus 1 into c, which is nothing but xy minus c equals to 0. Therefore, general solution of the given differential equation is y square minus x square minus 2c into xy minus c equals to 0. Now, problem number 5. Solve p cube plus 2x p square minus y square p square minus 2x y square into p equals to 0 by solving for p. It's a cubic equation. If I take p square common, I get p square into p plus 2x term minus, if you take y square common, it is y square into y square p common, it's y square p into p plus 2x. So in these two things I have p plus 2x common. So take p plus 2x outside, it is p square minus y square p into p plus 2x equal to 0. Again here I can take p outside, so it is p into p minus y square into p plus 2x equal to 0. So three possibility, p equal to 0, p minus y square equal to 0 and p plus 2x equal to 0. Consider one by one, integrate it and solve. First, p equal to 0 implies dy by dx equal to 0. You directly integrate it to get y equals to constant as a solution. So, solution of p equal to 0 is y minus c equals to 0. Consider p minus y square equals to 0, which is dy by dx equals to y square. Separate the variables, dy by y square equals to dx, integrate it. Integration of 1 by y square is minus 1 by y, that is equals to x plus c. Cross multiply and simplify it to get y into x plus c plus 1 equals to 0. Now consider the third factor, p plus 2x equated to 0, p plus 2x equals to 0. Same procedure, separate the variables, integrate it to get the solution y plus x square minus c equal to 0. Product of all these things is a general solution of the given differential equation. Now, problem number 6. Solve x square into dy by dx whole square plus xy into dy by dx minus 6y square equals to 0. Given differential equation is x square into p square, dy by dx is p square plus xy into p minus 6y square equals to 0. As usual, it's a quadratic equation. You can find its factors. and solve it for p to get roots as p equals to 2y by x and p equals to minus 3y by x. Equate it, px minus 2y into px plus 3y equals to 0, and then solve them to get solutions as usual. Y minus x square by c equal to 0, which is a solution of px minus 2y equal to 0, which is obtained by separating the variables. And solution of second differential equation, px plus 3y equal to 0 is x cube y minus c equal to 0. Therefore, general solution is y minus x square c into x cube y minus c equal to 0. So, with this I will stop this session. In the next session I will solve some more problems on equations solvable for p and also x. Thank you.